Okay, so we started this example last time, and we we have this load of 100 kilomole of binary mixture, and this is 50% at the initial concentration, and this is binary system, of course. So we have, this is W0 and this is X0 as a function of time. He wants you to in fact generate the graph, so generate the function, draw the change of each of the following parameters with time. So he wants you to do something like this. So you have the time here, and he wants you to see what happens to the temperature in the still pot here. As we mentioned before, this is the still pot and this is the distillate. So this is your at time 0, and this is your W and XW, so they are changing with time. He wants you to see the temperature here, what's happening to the temperature here. So he wants the temperature. He wants also the instantaneous vapor composition. So he wants YD as a function of time. All these are changing with time. Still pot composition, XW also, he wants W. And the average total distillation with the average here. And he's actually assuming the constant flow rate of D, so it is basically equal to 10. So this is your D equal to this value. He is also given the relative volatility 2.41 plus the equilibrium data, in which we will see how the temperature will change with the composition, because you know this is YD and this is XW here. So once you know, for example, XW, you can get it from here, the temperature, as we did before. And it's very straightforward, I think. Based on this one, we said since we want to draw, we wanted to generate the data here. So we know the starting point of my X is 0.5, so I will start with some number below 0.5 because we know the concentration or the composition of the more volatile component in the distillate, in the still pot will decrease. So we started with 0.41, and then we said it's up to you. Maybe you want to start with 0.4, 0.3, whatever you like. And here, since you know the relative volatility, you were able to use this equation. And this equation is basically the integration. This one is representing what? Representing the integration of dx over y minus x from x0 to x0. But since we know the relationship between x and y in terms of the relative volatility, we were able to get the analytical integration. And we found W. Once you have W, I think the rest is going to be straightforward, because you will use that W at each x here to get, for example, the time. So now you have the time. So you have the x now, and you have the time, and from that you can have the other parameters as we did before. So we can have the W, you have the equilibrium, which is YD as a function of x here. At each x we have some YD, and all are related by this relationship. Again, you can have also the average from the equation, and all these equations were derived this morning, so we know how these are developed. And this is also a function of W and X here, so you already have X and you have W, so you can calculate average as at each X here. That means at each time. Once you know that, I think it is the last thing, which is going to be the temperature. At each X, you can get the temperature. As we said here, at 0.5, you can go, and you'll find this is your temperature. Or if you want to use Y, it's also okay. So 0.664, somewhere 0.664 here. But you have to go up to this line. And again, you will find it's the same temperature. So it's up to you whether you want to use this point or this point. It's up to you. But there's no need to use these two lines because it's a waste of time. So now you have the temperature, you have average, you have Y, you have W, you have everything. As a function of time, you can draw. And as you see here, the only thing that's going to increase is the temperature of the steel pot because the concentration of the heavy component will increase, and therefore the boiling point of that mixture will increase because you will have to have higher temperature for that heavy component to be able to evaporate. The other variables are going to decrease because all of these are representing the composition or the concentration of the more volatile component. And as you see here, this is the as average. You have the instantaneous composition of the vapor and instantaneous composition of the liquid, and these are two at equilibrium, of course. Okay, so every time this one, for example, or this one is at equilibrium, this one and this one at equilibrium, and so on. Okay. Now he's trying to see if we don't have the relative volatility, or if we want to use the equilibrium data given in the table. So what we do, so if equilibrium data is used, this is a possibility that you see in the exam. You are not given the relative volatility, but you will be given the equilibrium data. So in this case, your concern is how to get this one. And now this one is just the integration is basically from calculus A to B. This one is representing what? What is this from calculus? What is this term? What is the integration from A to B if of x dx? What is the value of the integration from A to B if of x dx? What is this? Any idea? If you have a function from A to B, want to get the integration, what is this called?
The area under the curve.
Okay, that's fine. So guys, please wake up. This is the area under the curve. And the area under the curve can be obtained numerically, as you know, from different approaches, from different tools. So all your concern is how to get this one numerically, because you cannot do that analytically. You cannot expand this equation. It is only numerical integration, and the numerical integration here is basically going to give you what? Area under the curve. So now the area under the curve is basically either you can do it manually, like for example, you can divide this one, for example, and you get the area here and you get the area here. So that will be, it's very similar to what you had before in thermodynamics. If you still remember, W reversible is equal to PDV, if you remember. And we use it sometimes if this one is not constant, if it's function of dv, or if it's function of v, we can get the area under the curve. That was in thermodynamics, and it was the same idea. So all what we're trying to do now is to utilize the equilibrium data that we have to obtain the area under the curve. So the solution will involve numerical integration to determine the value of W at different values of X. So now the area under the curve from x0, because we're starting with 0.5 to any given value x, we can use the same points that we generated. For example, if you want to use the same x here, you can start with x 0.45 and then 0.4, 0.35 and 0.3 and so on. The same points, and at each x you will have to find the area under the curve of this. Now, in order to do that, you can do it manually. You can go and find the area under the curve. You draw the 2 points, or you can use trapezoid rule or one of these rules. So numeric integration, you can use trapezoid rule, Simpson 1/3 rule, or Simpson 3/8 rule. And this is the general idea. Now, it is not limited to this one. It's up to you which one you want to use. But this one, just I usually do the calculation using this one. The minimum points, again, at the minimum points that you'll have to generate when you solve any problem like this one will be 4 points. Okay. Usually, or typically, the question will be asking you, for example, to calculate the composition, for example, if 50% of the distillate, sorry, if 50% of the feed is evaporated. So in this case, how much is going to be W here? It's going to be 50 minus 50% of the feed of W0. W0 minus, sorry, 50% of W0. So it's basically going to be half of this will gone. So you will be given W0, X0, and then you will do trial and error until you get this calculation, or this value, which is the natural logarithm of W over W0. Now, if you're happy with trapezoid rule, that's fine. If you want to use one of these rules, it's also fine. My advice to all students is to go and try to record the equation for the trapezoid rule or any other rule that you wanted to use in your calculator, and then you can generate the points, and then we will see how we generate the table in just in a moment. So now what we're going to do, we will start with at different x's, and as I said here, you can start with 0.45 from here, because at these values we know everything here. Okay. So now you're going to get y. You will have to get y here, because area under the curve, as I mentioned before, is going to be here x, but in the y is going to be 1 over y minus x. So at each value of x, I have to go to the equilibrium data, I'll have to get y, and then I have to get this value. So this is exactly what you have to do. At, for example, 0.5, you have the equilibrium. From the equilibrium line, it's going to be 0.7 something. At 0.45, it's going to be somewhere here. The 0.6, as you can see, 6.5. And 0.4 is going to be maybe 0.6 here, and so on. At each point here, you get y. Now you know x and you know y. You can get this 1 over y minus x. You get these numbers here. Now, integration using a trapezoidal, as I said, you can apply the trapezoidal rule if you want, or you can use any other rule you feel more comfortable with. But all what you have to do is just to get this number. So now what you have here, you have x, this is x, You have x here, which is point, I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 0.5, 0.35. So you have x and you have f of x. So this is your f of x here, and this is your x. And you can go back and you can see what will be the integration. So for any function now, y is basically f of x here. Okay, so it's 1 over 2 multiplied by h, and then you can y0 plus 2, y1, z1, and so on. I think you can find it in a different, written in different forms, but uh, you can, as I said, you can use this one, or you can use any other rule that you feel more comfortable with. Once you know this w, خلاص إذا أصبحت العملية is pretty similar to what we did. So the whole numerical integration we need is just to get w at different values of x. Once we know w, we can go back to the same equations as we did before here. If you remember here, you see here, plus once we did this one, the rest is going to be the same equations now. I know w at different values of x, I can get time, and I know w, where's that? And I know, yes. Now here, we already did that from the equilibrium data, but I know the y average. I can use the x and w at each point to get y average. And I can get the temperature as well, which is the same, I think. Doesn't change that much. Okay, any questions so far? So this is the typical procedure that you should follow, but let me just tell you what sort of problem you would expect. Maybe let me, instead of this one. Yes, I would go ahead.
Doctor, I didn't understand the point that you said we have to do trial and error if we have 50% of the.
Yeah, that's what I will explain now.
Okay.
I'll go through it now. So now this is what we solved it before. We were trying to generate x's. So we assumed we're going to have x's. Now let's assume for the same problem here, okay, for the same problem, he will ask you to calculate the time required to evaporate, let's say 30% the initial feed for the same specification. Now the specification that I have before is, let me get it here. Yeah, so I have W0 is equal to 100. And I have X0 is equal to 0.5. And let's assume D is again constant, given as 10 kilomole per hour. And he wants what is the time required, was the final, that will lead to evaporation of 30% of the initial feed. So what does mean? Means W will be what? Will be 100 minus 30% of the 100, which is evaporate 30% of this one. It's going to be what? Sorry, 30% is 30. So it's going to be what? 70 kilomole. So now I have W, okay, but I don't know X here. What X? We don't know. X at what? At W is equal to 70 kilomole. It's not given. But I still have the same equation اللي هي ايش اللي هي governing equation اللي I will be using, which is this one. I know for this simple is going to be x0 is going to be 0.5 up to x, which I don't know, dx over y minus x is equal to what now? Is equal to ln. The equation says w over w0. I know w and I know w0. Where's w? W is 70. W0 is 100. Okay, so that means this integration from 0.5 to x dx over y minus x is equal to what? Ln 0.7. Now, I have an equation here. The only unknown I have is x here. So what I will do, tell you that. I will start with my x here, let's say 0.45. Okay, now let's say we have x0, we start with 0.5, and w here is going to be 100. Okay, now the second one is going to be, let's say 0.4. Okay, now when I have x is equal to 0.4, I have to take this x here and I use it in this equation. Now if I have x now, I can get the integration, صح or not? Is that clear? So when I know the x now, because I have to go step by step, I will say, okay, now I move down to 0.4. So now there's no need to emphasize this fact that you cannot go above 0.5. You have to go down. So let's assume you go 0.4. Now once you have 0.4, you can get this integration term. Huh? From the integration term, you will see whether this integration term here will give you the same value as ln 0.7 or not. If it is going to give you very close value to 0.7, that means this is your x, which is not going to be okay. You will need to go more than 0.4, maybe 0.35 or 0.3. So again, so you start with 0.5, the initial, and you know 100. Okay. Now you go step down one step, maybe 0.4. Maybe someone else will go down 0.45. It's up to you. But the main issue is going to calculate W. W, where do you calculate from? Calculate from this one. Because you're going to have ln W over W0. Now, once I know the integration here, once I know x here, I can get the integration of this one. And I know W0, I can get W. And I put this W, let's say it's going to be 90. I found it to be 90 or something. Should I continue or I have to stop here? I will say, no, I still have to go a little bit further because my W must be what? 70. So I go another step. I say 0.4, let's say 0.35, let's assume. I use this number and I do the integration here, again with the new value of x here, and I get W. And I'll check W whether it is, let's assume it was 80. So that means I should continue because I need to have 17. So if by any chance I went to 0.3 and I use this 0.3 in this equation, And then I found this number here. Because I know now x, I can get the integration. And this number given, and I know w, 0, I can get w here. Let's assume it was found to be 70 here. Now I have to stop here. And this is the last thing. This is the last point. What I get from this one, I go to the equation, use it for the time. Do you know the equation? Yes, I know the equation. The equation says time is equal to W0 minus W over D. Okay? What about the X? X calculated here, last one is going to be the X at this time. And you can calculate everything else. Maybe you want to calculate also, even if you want to calculate the Y average, you can say Y average is equal to X0 W0 minus XW over W0 minus W. So now you already have X0 W0, and now you determine X and W because you know W, but you determine X, that will give you W. A little bit interconnected here. So you have to continue going down one step at a time until you reach that W. Given in the statement of the problem to be 70. How I know it is 70? Because he says it will time required to evaporate 30%. That means you're going to evaporate 30% of the 100. That means what is going to be left is going to be 70. So you're going to go down step by step in terms of x, and at each x you will find the integration, and from the integration you go in and find this term ln w over W0. Now you have w, and knowing W0 is given, so you can do the exponent here and you can get w. Until w reaches 70, you stop. If not, then you have to continue. If you by chance you find out w at some certain value of 4.3, you find it to be, for example, if it was, for example, at 0.3, we find this one is, let's say, 60 here. So we have to go back and adjust this one, and we will work with 0.34, for example. And that's why we call it trial and error. Until that number W is close to 70. I'm not expecting you to get the same value of 70, but it should be, for example, 96.9 or 70.12 or something like this, around this 70 value. Because, you know, this operation involves integration. And integration, especially if it's a numerical integration, accuracy is something that you're not going to guarantee. Okay, this is one typical problem that you will see. Another probably example, or another typical question that you might see, maybe regarding the time. He will tell you what would be the composition of your or average composition. He might ask you, what is the average composition of the product after 2 hours? So again, you're going to do the same calculations until you reach 2 hours. Now 2 hours means what? You have to go back to, now he's not giving you the W, he's giving you the time. Now it's 2 hours. Now what do you have to do? You come to the equation here. Let me wipe some of this because it's become, so now if it was like, for example, what is the average composition of the distillate after, let's say, 2 hours? Now, all what you have to do, you go back to the equation for the time, and you know the equation for the time already derived for this model. And the equation says the time is equal to what? W0 minus W over D here. Now, I know 2 hours here, and I know D is 10 kilo, so I have to say now this is, sorry, this is 2 hours, and this is W0 100 minus W is the one that we wanted to calculate over D, which is 10, hopefully will work out. So now you're going to have 20 is equal to 100 minus W, and this will give you W is equal to what? 80 kilomole. So you will have to do the same procedure. I explain it now, and you will try to generate this x here from 0.5 to the value, to that x final, let's call it x final, that will correspond to what? To W to be what? 80. Once you have x and W, you can go back to the equations for the, for example, for the y here, and y average. Y average is basically what? Is going to be x0 W0 minus xw, you know x now because this is x final, divided by 100 minus w, you know w, what is the value of w. So you see here the equation or the equations that we develop, it can be used interchangeably, but all the time, in order to evaluate the integral part of this equation, which says the you have to generate this x here. Sometimes you will be given also x. He will tell you, for example, what is the average composition of the distillate when. What he say? What is the average when x is equal to, let's say, from 0.5 to 0.1. So now it is more easy. There is no trial and error. All what you have to do, you have to divide it 0.4, 0.3, 0.2, 0.1 here.
Dr. Faria, did you see Dr. Faisal? He's around or Dr. Ijaz? Oh.
Sorry. So as you see here, there's no trial. All what you have to do, you don't know x, you don't know w. All what you have to do, you have to generate this table until the final xf. Okay. The xf in this case is given as 0.1 here, so you don't have to try it on xf. All what you have to do is just fill up this one, base it on the equation, which you already used, the main equation of this batch distillation. That says here, it's written, let me just, yes, integration from x0 to x final, dx over y minus x equals ln w over w here. So at each x here, you're going to find w. That's the way how we did it in the previous examples. Okay. Any questions? I know it is a little bit confusing at the beginning, by the way, but the more confusing stuff is coming in the way, inshallah. And this one is very straightforward. But what we're going to do next, now we have only a pot. It's like we have a boiler in which we're adding heat and we're generating steam. It's not steam. We're generating vapor, which is at equilibrium with the liquid, and we losing that or we decreasing the quantity of the initial feed, and at the same time we try to concentrate the more volatile component in the distillate. Is there any comments or any questions? Is this clear or? So this is the simple, and we will, inshallah, in the tutorial session, we will show you how to do it. And that's it. Now, when the next topic is going to be also batch distillation, but as I explained before, in this model that we wanted to discuss together now is when we have stages above the still pot here. Now, this is what we had before. This is exactly what we have. And we said XW and XD at equilibrium. Now, you might ask yourself, what this guy is saying here, this XD is liquid, and this one is liquid. Where the equilibrium is? Why we say at equilibrium? Do you know why? Why we say XD and XW at equilibrium, even though they are both liquids? Do you have any idea? Why is it possible to claim XD and XW are at equilibrium even they are liquids? They are liquid. Why is it possible? Think about it. Any idea? No?
Doctor, there are different components, right?
Why it is possible to say they are at equilibrium? I know they are different in the composition, but why should we be allowed to say they are at equilibrium? Do you remember when we discussed this one? Distillation column. We said this is, let's say this is stage number 1. And we have vapor here with Y1. And this is XD, and this is X0. And this is total condenser. Okay, we said Y1, okay, is equal X0 is equal XD. صح? Is that true? Is this claim okay? Y1 is equal X0 is equal XD. When we have total condensation?
Yes,
Why is that?
because the whole vapor condensing.
Yes, because we basically have the whole vapor is condensing. And all what we're doing here, we're just splitting. We have splitting point here. So basically, splitting point will change the flow rate. So now, for example, D, now here V1 doesn't equal L0, is not equal to D. But their composition are the same because we have splitting point between these 3 streams or 2 streams. Now, okay, let's follow up this. Now I have Y1 from stage 1 and X1 here. So now X1 and Y1 are at equilibrium. So is that true?
Yes,
So that means x1 is at equilibrium with x0. So we're saying it's at equilibrium because simply here, because xw is at equilibrium with this y here. And since y is the same as xd, so we can say xw is at equilibrium with xd. So we're saying that just because we have complete condensation, we're totally condensing all the vapor going up. So that means the composition here and the composition here are the same. And since the composition or the vapor leaving this pot here is at equilibrium with xw, so that means xw here, equilibrium with y, and y is equal to xd, because total condensation, that means xd and xw at equilibrium. So hopefully you understand this principle. Okay, so now we said, therefore, at the simple model here, we have xw and xd are at equilibrium, يعني related by, let's say, y is equal to kx, a simple model. Now the other scenario, if we have something between this one and this one, and which is going to be the rectification section. So we have stages now. We have maybe 1, 2, 3, 4, 5, and so on, up to n here. Can we say xw now and xd again at equilibrium, even have total condensation? Can we say that? Can we say now again in the rectification, when we have a rectification, can we say that xw again is at equilibrium with xd?
No,
Good. Very good. No, why not?
because it's not splitting point. يعني.
Yeah, because it is not now xw. In fact, if we wanted to focus more on this, you see, xw is here is at equilibrium with the vapor leaving to the first stage, and the vapor leaving the this stage, okay, and this one is at equilibrium with this one. So this is x1 and this is y1, okay, and this one x2 and this is y2. So you see here xw has nothing to do with xd, okay. But what do you think is going to be relating these two from previous study? You remember when you have a distillation column, we have this xd and we have something called xf here. What we had here, what we call this one, rectification section, and what was here relating the xd with xf? I will remind you with this diagram here. The one that is relating the xd with x field, let's say in this case, was what? The stages. It will depend on how many stages we have. So this one and this one will be, or the relation will be a function of how many stages we have. If I have no stages at all, then they will be at equilibrium. If you're going to have only one stage, then that will be my xcw. If I have, this is the operating line, will be function of what, guys? Will be function of the L0 over D. So that will be my reflux ratio. So at each reflux ratio, if I have, let's say, 2 theoretical stages, and then my XW will start with XD here, and I will say this is my XW. If I have only one stage, I will say this is my XW. If I have 3, I will say XW. So you see, XW is function of the slope of this line, which is going to be reflected by L0 over D, and also by the number of stages I have on top of this still point. Is this principle okay? And this is what we wanted to explain in the next slide. So in here we have this equation again. We still have the same equation now, but as you see here, the x now and y are not related by equilibrium anymore. They are not at equilibrium, but they're related by what? Related by this. You see here? And this is x0, of course, between the stages. Why stages? Because in this case we have, let's say, we have two stages. Okay. And also with the slope. So now if you want to find out the integration here, you will have to generate a table. Okay. Now you are going to assume for constant reflux, if you want to assume, what does constant reflux mean? Means you have slope constant, but your x will change. You're going to have different values of xd because you want to keep the same reflux. If you want to keep the same reflux, your xd will change. And since your xd will change, so at each xd, you're going to have xw because you're going to have the same number of stages. So at, for example, this one you have 2. This is your xw0 and xd0. Now you move a little bit down to another xd. You're going to have 1, 2 stages. This is, for example, xd2 and xw2. You have maybe for let's say you have here, let's say, for example, you have somewhere here, matter. Try to be accurate, but if you have at this point, you're going to have 2 stages, so that's then you're going to have xw, another xw, maybe, but you cannot go beyond the xd0. You can't go here. Maybe you come here and you can say you draw this slope and then you go move 2 stages. So you have another x here with the xd. So you're going to have bunch of table. From this data, you can get 1 over y minus x, and you can find out w based on the initial charge of your field. It's a bit confusing, I know, but it is. It will be very clear when we solve one of the examples, inshallah. But as you see here, the main difference is that the flux ratio is constant, and I have some stages above the still pot, the main pot used in the sample batch distillation. We'll continue, inshallah, next Wednesday. We'll see maybe one example or two, and then we finish it with the tutorial session, inshallah, on Monday, next Monday. Any questions? What's this fashion? Rakbak? I don't know. Oh, sorry. Thank you very much, Claire. Okay, so that's all right. Okay. So if there's no more questions, please don't be scared. This is it's going to be very simple. I think you just have to go revise the trapezoidal rule used to get the integration. So, but otherwise, it's very clear, very straightforward. Inshallah. Okay, so the quiz, I will remind you again, is going to be on Thursday at 12 midday. Okay, and it's going to be on multi-component distillation. Pretty straightforward, but make sure you solve the question you see in your screen. Then I will probably you will see every student will have his own number. So the same equations you're going to use, everything is the same. but maybe you will find a little bit difference in the numbers. So if you're going to copy from your colleagues, you will be penalized at 0. I don't want you to do, because this is your chance to compensate for the previous quiz. Okay, guys, if you're going to do, for example, any iterations, I think you don't have any iterations except when you're going to find the psi. Please, if you want to use a calculator, you don't have to show me all the steps for the iteration, but all what you have to do is just write down the initial, the starting iteration point, and then you can write the final answer you get from the iteration. Or if you want to use the solver, now if you want to use the solver, fine, but don't do all the calculations in the Excel sheet. I want you to, please guys, I want you to write it in manually, please. Okay. Thank you
Doctor,
again.
Doctor, you mean the initial guess
Yes.
and the initial
Just
conditions?
to, sorry?
You mean the initial guess when you said the initial conditions?
لا initial, I said initial guess, sorry, not initial condition.
Oh, okay.
So when you do, because you only have one iteration, I think, step in the multi-component distillation is where you're going to find the psi. And that's the only way, the only position where you have to do iterations, but otherwise everything is, I think, تعويض مباشر يعني. Okay, guys, thank you again very much, and see you inshallah on Wednesday. Continue our
Doctor,
journey.
I have a question before you leave.
Yes.
Doctor, what do you think that we will have for the test?
For the test.
Yes, this chapter also.
Well,
the previous chapters.
I think yes, it will be mainly on distillation, I believe. And by the way, the test will be on campus. Huh? Do you know that?
Yes, yes. I was asking about.
You ready with the masks and everything? Sanitizer.
Yes.
Yes.
So this is going to be
Doctor,
very
what
good.
is the date of the test?
Okay, good question. I will tell you exactly the date now. Can you wait here, because I just received an update regarding this one, but because let me just okay, I think I will tell you right now. I was going to announce it just where's that sheet? What's that? And the open moderation test one. Okay, I have to go to this folder. This is the problem. To this midterm room reservation update. This one, I guess, here. Okay, so 313 is going to be 29th of November. Okay, and it's going to be in Hall 15. Yes, so it's going to be the 29th of November. Means when it's going to be. Let me tell you exactly when. Sometimes the numbers are not. And 2 weeks time. Not next week, but it's going to be the week after next week, Monday. And it is going to be only 1 hour, I guess. And that's what they allocated for us from 1:45 to 3:45. But we have to leave 1 hour before the end of the test. So they said because they have to do sanitization and stuff like that. Yes, Bushra, what?
دكتور الكويز يعني كان 35 minutes وما كفى وهو سؤال واحد يعني ساعة.
وهذه للأمانة أنا أتفق معك 100%. To be honest, يعني I agree 100%. I don't have to argue with you. Like, and this is what we have. So we try to maybe we're going to avoid the function somewhere. Maybe we give you just makeup, or maybe we give you a little bit of makeup and a little bit of. We try to avoid any question that would require too much time without any ideas, because.
دكتور لا تعيشنا على الأمل. لا تعيشنا على
والله
الامل.
هو انا شايف للامانه يعني to be honest يعني حتى الاخطاء اللي what you mistakes I saw in this في الكويز الاول ما كانتش المفروض تحصل يعني بصراحه يعني لان هو ممكن التايم بس I don't know to be honest يعني I don't know يعني لكن I promise you والله هي طبعا محيره حتى لنا احنا to be honest يعني we still thinking
دكتور
of
ما
how we
تصير تخليهم دكتور ما يصير تخليهم تفتون وتفتو، لأن ساعة واحدة وعلى 30 درجة شوي يخوف.
والله فعلا هذه لان احنا حتى ناقشنا الموضوع. احنا لما اقترحوا علينا في البدايه على اساس ان احنا نعمل كامبس، فكان متوقعين ان حنكون عندنا at least 2 hours or يعني 3 hours or at least open. وانا احنا ناقشنا هذا الموضوع، انا كلمتهم يعني وشرحت لهم ان احنا في some courses requires more time يعني احنا مش it's not مثلا تشينج 1 يعني او هذا كورس يحتاج الى رسم، وهذا الامتحان بالذات عليه 30، فحرام الطالب يعني بصراحه 30 محتاج 1 اور يعني احنا كويزز بناخذ عليها احيانا 1 اور up to 1 اور. ف to be honest we haven't finalized yet what exactly going to be in the test. فاحنا نخاف ان احنا نعمله very simple لدرجه ان everyone will be able to get the 30 which is not fair also لان some people are working hard. فاحنا we try to يعني optimize بحيث يكون at least 50% will get full mark at least of the 2 sections of course. But at the same time we don't know, maybe we can يعني 1 hour I feel under this stress, but maybe we say because we're going to be with you the instructors it might be more easy يعني it's not like online you have your instructor with you. If you have any questions you will get feedback immediately, so we're still thinking of something that will not really harm or at least will not be very tough لأن عليه 30 وإحنا we don't يعني صراحة we're not happy to see students getting too much يعني low يعني. rest assured we'll do our best we are flexible يعني it's going to be a test يعني. والتست ممكن احنا اذا كان مثلا لقينا عليه انه هو الاوفرول بيرفورمانس is not good enough ممكن ننقص، ممكن نخلي عليه بدل من 30 ممكن نخلي عليه 20 فقط يعني ونوزع الباقي على الاساينمنت وعلى الكويزز. فهي it's not the end of the day يعني it's not خلاص يعني 30 حيبقى 30 لا احنا ممكن we can adjust it if it is very poor يعني.
بس دكتور it's not fair يعني for us لو مثلا الكويزز يعني في شيء ناقصين.
quizzes we will take the best of 3 يعني. quizzes we will take the best of 3. فأنت if you fail in one or at least if you don't do good in one quiz يعني you should be able to make it for the other quizzes. فإحنا في quizzes we will take the best of 3. And you will see for example quiz number 2 it should be easy يعني I don't think there's any unless you didn't attend any lectures يعني. فبي prepared. السيبريشن كورس 2 بالذات يعني ما فيش اي افكار للامانه، هو كله وقت تايم كونسيومينج يعني by the way it's nothing to be honest there's no any ideas it's just follow the procedures like cooking book يعني follow the procedure the practice more try to يعني get used to the drawing because هو كل المعضله انا as I mentioned at the beginning of the classes I told you guys مش هتلاقي ان في فكره غلط يعني لو انا اعطيك الجزء الاول واروح اقول لك بروح اجاوبه هتجاوبه 100% يعني ما فيش اي فكره اللي هنا ما فيش يعني يعني لو جبنا اي فكره معناها مش هجاوب ولا واحد سؤال. ففي العاده احنا بنجيب نفس الافكار اللي شرحناها في الكلاس بس بنغير الارقام. بالتالي who is going to be able to score 100% اللي هو تمرن على it's like when you are having a match تستعد prepare very well حتبقى لياقتك عاليه جدا you will perform well. مش هتلاقي اي فكره جديده يعني هتلاقي سؤال انت شفته ممكن مجاوب زيه بس هل مجاوب زيه باليد ومانولي وعملت الرسم باليد ولا انت جاوبته بس بالنظر؟ لان احيانا في الطلبه في بعض الطلبه لما بيراجع الاسئله والامثله او الاشياء بيراجع الافكار بيقول لك اوكي الفكره هي معروفه خلاص يخلص شوف اللي بعده بس هو ما جرب بيده ولو لما تجاوب المساله بيدك هتكتشف انك انت عندك في صعوبه time consuming. Okay, it's like in the TOEFL and the IELTS test, English language proficiency. تلاقي ان الاسئله مش صعبه، بس الوقت هو اللي ما يسعفكش لانك انت مش متمرن. You are not prepared. Please, my advice is to solve حتى المساله اللي بتعرف فكرتها go and solve it. Draw everything by hand. في حاجات انت بتشوفها سهله بس لما انت تجي تحاول تعملها لوحدك هتلاقي روحك no it doesn't work with you، لان في شيء فات عليك او شيء little thing مرات احيانا very simple thing انت كنت متصور بشيء هو في الواقع شيء اخر. اوكي.
Okay,
Any
thank
other
you,
comments?
Doctor.
Okay, then I wish you all the best. I don't want to waste your time more. We already passed the allocated time for us. Thank you very much again and see you inshallah on Wednesday. Okay.
Thank you, Doctor.
Thanks, guys.